Hey everyone, welcome to our, wow, it's already episode 10. This means that by the end of this episode, we'll be hacking on this project for 25 hours already. Wow, that's a lot. And yeah, we got some nice progress. So this is like, for those who may have found this on YouTube or something, we are hacking on Raspberry Pi Pico simulator. We have been doing it for almost 2 months, I think, or actually more if it's episode 10 and this is like weekly. So a bit more than 2 months. And before we begin, just let me know, as usual, in the chat if you can see and hear me. Meanwhile, I will start by sharing my screen. Thanks, Nekadi, and hey, Steve, good to see you here. Okay, so last time we managed to get GDB to be able to debug the program. So GDB is the GNU debugger, a very powerful debugger. So now it's able to debug the program that we have in the running in the emulator that we are creating. And we even managed to get it to work with Visual Studio Code. So yeah, let's see what we did, because I don't remember. I haven't touched it the whole week. I did take a look at the Raspberry Pi Pico datasheet again, just to learn a bit about interrupts and exceptions, because I have some feeling we may need to implement them today. So now I'm a bit more educated about those subjects, but I haven't touched the code in a week, so I don't really, I need to refresh my memory. So first of all, let's see. So we have this Visual Studio Code. We did this configuration where it starts GDB, and I guess we need to start a project so it can connect to it. So let's npm start, and let's, a lot of output. Yep. Whoa, breakpoint. Yep, probably. Oh, right. We have a different entry point for the GDB, right? Start GDB. That's what we need to do. npm start GDB. npm run start GDB. Let's make the font size even larger. Okay, cool. So GDB is running and it's on my Windows machine. And now I'm going to connect to it from my Linux on Windows subsystem for Linux machine. Okay, and here we are. We have this GDB, and we can see inside Visual Studio Code where we stopped, I think, or maybe we can't. What happens here? Flash binary start. Yeah, that sounds like we are at the very, very start of the code platform entry. So yeah, so probably, let's see the code. So probably gdbserver just waits for GDB to connect and it doesn't even run the code. Yeah, it just set the PC, and I guess we don't do anything until GDB tells us to execute the code. Cool. So let's continue, and then it should eventually fail on that assertion that we have there. I mean, yeah, it failed, and now we can finally have this nice debugger interface where we can try to figure out why it failed. So this is, or is it a breakpoint that we have set? I think, yeah, we have set a breakpoint last time. So it's a moment before the assertion failed. So we can actually try to see what's going on here. So we have like a handler. And then it compares some value it reads from the vtable with this handler. This is like setting a handler for specific IRQ interrupt request, specifically number 3. And if I'm not mistaken, IRQ number 3 is defined somewhere in this humongous datasheet. Maybe there is like hardware alarm set callback. And what is this IRQ number? Where is it coming from? Hardware alarm IRQ number. So probably there are like, yeah, timer IRQ 0. So it's trying to set up a handler for the first timer IRQ, and that's actually for number 3 before, because we have number 3 and it starts with 0. And then this code is trying to read some data from this vtable. Let's step into it and see what it's doing. So step into, and nada. Is it like running very slowly, or is it dead? Okay, yeah. So now we stepped into it. It's not the fastest interface in the world, but it's still useful. So yeah, so we are inside this function, and it returns just vtable at location 16 plus num, and I guess vtable, yeah, is just this VTOR that I remember we have seen in the past. Okay, cool. So first of all, let's see what this returns. I guess it will return all Fs, because this is like reading from some uninitialized memory, but let's see that. Let's step out of it. And oh, this is slow. I wonder if there is a way to make it a bit faster. But we can already see that current is all Fs, and unused IRQs is not sure. Let's try to. So the nice thing here, I also get is debug console, where I can just type expressions and see their values. So it seems like this is the value of unhandled user IRQ. So it's reading from some memory, and it expects to find there probably this unhandled user IRQ, but it's not there. Let's try to figure out who puts the value there. It's probably, so this is where it's defined. And do we have, what is this code? IRQ remove handler. IRQ, maybe we can just use Visual Studio Code features to find all references. That's not very fast as well. Yeah, we want to look at the SDK, not the boot ROM. I think that would be just faster to So this is inside removing the handler, but I guess there is something that should initialize it to IRQ. Yeah, okay, so probably this function should do it. IRQ handler chain, or maybe, no idea. Okay, so there are like 2 options here, I think. First of all, it's possible, so we have this IRQ get vtable handler, and it's possible that we are just reading from an invalid memory location. So this pointer points to an invalid location, and that's why we are getting garbage. The other option is that this table should have been initialized somehow, but it wasn't. So let's start by trying to see what value this returns. So we'll just stop the debugging session and start the whole thing over and start it again. And hopefully we will get into this breakpoint and we'll see what is this value that vtable gets, if it makes sense or it sends us to something that doesn't make a lot of sense. So callback, yeah, This is like the first breakpoint, I think. Yeah. And then, why did they set a breakpoint here though? I think this is like the interesting place. Okay, so this is probably inlined, but maybe I can call it from the debug console and see what it returns. And I just synchronized the changes on Git, which might not have been the best thing to do. Okay, so let's try just to print the thing that's inside it. Maybe it will work, like this expression. Unable to create variable object, but I want to see this value. Still unable to. So the thing is, we're probably compiling it with some compiler optimizations, and it causes stuff like function inlining. So maybe another approach would be to remove those, to compile it without the compiler optimizations, but I will give it another go. So we can also run gdb commands from this with -exec from this debug console. So we can try our luck with gdb. Maybe that would work. Could not write to register xPSR. Yeah, I think I think we forgot to implement that register. So let's do that. And that might fix printing here. We probably need that anyway. So yeah, so we had like, I think this to do here, where, yeah, which is blah, 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 figure B1 in the ARMV manual. Let's go there. ARMV manual. Right. Probably here. ESPR. xPSR register layout, but all right. (32) that comprises of 3 sub-registers. Oh, I got it. So these bits probably go here, and then we have this and these bits, and then we have this part. So we already have like this, so we can probably return those. So let's change our implementation and create a setter and getter for this spatial meta register. That's get. They call it xPSR. Yeah. Get xPSR. So maybe for that we would need to implement another helper that would return the status register APSR, just to make the code a bit more readable. APSR. And if you remember, we initially had this register, but then we decided it would be easier just to store the individual bits as fields, as different members in this RP2040 class, just to make it easier to work with it, because every time we need to update a single bit. So basically, we just want to return this dot, let's see, n is the highest bit. So and then there is like z is the next bit, and c and v. And there might be a different way, more efficient or whatever to do it, but I think that that does the trick. And then let's make a setter for it. Set APSR value number. So it doesn't return, it just set those bits to if value and this, then we just want to convert this expression to Boolean, and that's the JavaScript or TypeScript way to convert an integer into, or a number into, a Boolean. Okay, so now we can start creating the getter for xPSR. Return this.APSR, and eventually we would need to OR it with IPSR and EPSR, but we don't have them yet. And let's make a setter APSR. So we can say this.APSR. Okay, that's x equals it equals value. I mean, we could like just masked out all those lower bits, but we don't care about them because we know our setter doesn't really look at those bits. Cool. And then let's take a look at this IPSR and EPSR. I think they are just like spatial registers. So I don't think they are like stored in the memory or anything like that. I think, yeah, probably like APSR, they are just like other registers, integer registers. So there is like xPSR, then there is like composite views, but I don't think, I'm not sure if we need to care about it. Anyway, so this is actually just two values, and this is like exception number or 0. So maybe we can just public IPSR, uppercase actually, and it starts with 0, and then we can also like set it and update it when we are looking into xPSR. So and we'll take care of you in a moment. And then this.IPSR is value, and then we'll just mask. It's like 6 bits, if I'm not wrong, right? 0 exception number, 0 to 5 probably. Otherwise, they wouldn't have mentioned 5. So it's 6-bit. So I think 3F would mask the lowest 6 bits. And then there is like 2 more bits for EPSR. Okay, it's reserved, but when the processor stacks the PSR, it uses this bit to indicate the stack alignment. Okay, and what is like the T? Okay, so EPSR contains the T bit, which indicates if it's in template, it can be read by software. In our case, we are always yeah, it might always maintain with the value 1. So oh, there is a question. Hey Punith, good to see you. There is a questions on yeah. So Thomas is asking about what extension I'm using to show the test coverage, and I will answer that in a moment. Let's just finish with EPSR. But great question. Thanks for asking it. So yeah, I think for the EPSR, we can just always return 1 here and just no, ignore this. So basically, we will just always return here 1. So that would be, maybe that would convince GDB. Remember that we had the that issue, not XS24, that issue where GDB was confused whether we are running on thumb or normal ARM. So maybe that's the solution. No idea, but we'll see. And this is reserved. I don't think we should care about that right now. I hope we shouldn't. Yes, R9 is reserved. Yeah, I think we'll ignore it for now and hope it doesn't bite us in the future. Anyway, so it seems like we have probably usable getters and setter for this xPSR, and now we can just return it. RB2040.xPSR. Cool. And when setting the register, I think if it's more than 16 now, because we now know to handle this, and then if register index is 16, then we just update rp2040.xPSR equals maybe we should just give it a new variable value, else this one equals value. Okay, so now we have this xPSR register implemented, and we will probably create a commit. But first of all, answering Thomas. So this extension is actually called Wallaby or Wallaby. I don't know how to pronounce it. And it's a really nice one because you can not only see the test coverage or the values. It has some very interesting features. Let me just show one real quick because we have some other interesting stuff to do today. But let's say I want to understand how a single test case, what kind of code it visits or it runs. So I can go to view story, and then I can see like all the lines of code that were executed as part of my test. So it's like all those highlighted lines were run when this test case was running. So this is like the entire code that ever executed from the moment this file was loaded into memory until the end of this test. So and then the story starts like shows me everything that happened, all the variable initializing, basically every line of code that ran. So I actually don't use this feature as much, but I think it's still cool. And then you can like travel back and forth, and it's like single stepping, but let's say it's not really interesting. But basically you can like sort of single step, but also backward, because you got this whole recording. And I think you can also see the values of variables, not sure. Anyway, it's a cool extension. I think it costs $100 a year per license or something like that, and I really love it. Okay, so let's create a commit. We added this IPSR and xPSR registers. So feed gdb, and that's how we call this, gdbserver. Add xPSR register support, and now maybe we will be able to call this function from within gdb and see what it returns. Maybe not. Let's see. Okay, so let's restart the debugging session and then wait for it to hit the breakpoint. Did I start the wrong thing, or maybe all those sprints are really slowing us down. Maybe that's the reason everything is so slow. We'll check it in a moment, how to disable them. But for now, I mean, we used to need them a lot because actually this is quite useful still, because it shows us where we are reading from. So if we step over this, we'll be able to see where it's reading from. But let's see if we can already do it from here or from GDB. So this doesn't seem very useful. It actually seems to have confused the restarted, or I don't know what. Let's try it with the p command of GDB. Yeah, it seems to run some code. Maybe it's running the code of get vtable, but then we get no output. So not sure what's going on here, but it's not doing what we want it to do. And if we step into it, probably won't get us what we want, but let's try that anyway, because I think we have a breakpoint here, but it never stopped here. So where are we right now? A lot of interesting writes, and I don't know, it seems like calling this function made the code go mad. Okay, so I'm going to try something a bit different, and instead of trying to debug it in the simulator, yeah, let's stop that for a moment. Let's try to see what happens when we try this with the one and the only Raspberry Pi, the real one. And I think on the Raspberry Pi I got this Blink program, so on the Pi Pico. So let's change it to, where is that Blink? It's Pico examples, build Blink. So probably this should change to Blink, and this should change to Blink as well. All right, and then I still expect like the same. Maybe let's do it like that. Let's put it as a comment. And by the way, you're welcome, Tomasz. I don't know how to pronounce it correctly. It has all those symbols above the letters, your name. Okay, and then instead of connecting to the WinHost, let's connect to the Raspberry Pi one. So this is like the OpenOCD I'm running on a Raspberry Pi that is connected to the Pi Pico to debug it. Okay, let's see if that works. And if it does, maybe, yep, unable to continue the process. Interesting. That doesn't sound very promising. All I wanted is just maybe sometimes there is like a monitor reset command that just resets the CPU, and it seems to work here. So maybe now I will be able to continue executing. No, seems like things are going bad when I try to debug it with Visual Studio Code. So, what is going on right now? Am I debugging? Not. Command aborted. See the output window. Where is the output for GDB? Is there one? Let's see. Let's try with the can't add a breakpoint. Resource not available. Oh wow. Maybe I got disconnected from the Pico or something like that. Let's restart. Yeah, it seems connected. Okay, let's restart the debugging session and see what happens now. I'll just put those side by side so I can see the OpenOCD output. A lot of failures. In GDB, targets need reset. Target extended remote. Okay. Maybe we can do that if it says we should. So, but how do I tell it it's an extended remote though in this? Anyway, let's try to reset the target. Monitor exec monitor reset. Didn't seem to do. Oh, we are not looking. Halted due to breakpoint. It doesn't seem like it's at the beginning of everything. Maybe there is some assistance in the Pi Pico manual. There is debugging, GDB. So yeah, we are here. Target remote, load, monitor reset init. Okay, let's try that. Monitor reset init. Okay, it did change the value of PC to something that looks like the beginning, so it's a bit more promising. Cool, let's try to play and see what happens. Can't find free FPB comparator. What is FPB comparator? Oh, maybe we are just getting, but we only added 2 breakpoints. We didn't, I think it even says when it starts that it has like 4 breakpoints, but then it doesn't even want to add 2 breakpoints. But let's try to Google that and see if there is anything we can do about it. And maybe we can close some of those tabs because they are probably not relevant anymore. Clean up all these. Yeah, this might be still be useful. We don't need that anymore, and I hope we are not going to need this disassembly anymore. Okay, so we are not the first one to get this issue. Load flash patch breakpoint unit. Okay. Starting registers. Oh, cool. I'm happy to much that I nailed the pronunciation. Just tried and it worked. Cool. Okay, so don't know if we want to get into this adventure of debugging this. Maybe we'll try just to start it with single breakpoint and see if that helps. So where are the breakpoints? Let's try to disable them all first of all and see if that helps in any way. So let's restart this thing and yeah, play it again and see if it's happier. Debug request. Okay, we are in main. Are we? Where are we? Doesn't look like main according to the PC. Let's start it again. And yeah, I can see the Pico blinking, so yeah, it's probably running, and now I stopped somewhere. But then, so without any breakpoint it works, but let's see if we can at least get 1 breakpoint. So I think that was the interesting one, but yeah. So let's try to set only this one and restart the whole thing and then play. Will it work? Or what happens? Oh, it can't add a breakpoint. Not fun. And here we are again, somewhere random in this. Yeah, so let's try a different approach. Let's try to use GDB without Visual Studio Code and see if that works any better. So basically we have this, I think, open from last week, this multi-arc GDB. So let's just clear it and let's go to the blink and run GDB multi-arc and then load this symbols file. Just so we have symbols and then target remote and not connected, so it should probably work. Yep. And we are at the beginning of the program, and now let's try to set this breakpoint. So it was inside irq.c line 18. No, yeah, 18. And GDB goes silent. Yeah, 5 locations. Interesting. Maybe that's a problem that it has 5 locations. Let's continue and see if it works any better. Too many. I only requested one, but why did it stop at break at 5 locations? Oh, I get it. So this function is inline, so there are probably 5 places where the same function is used, and since we only have like 4 hardware breakpoints, we can't install 5 breakpoints. So just breaking here is not gonna work. And let's be optimistic now that we figured that piece of information, and let's try to set a breakpoint where we call this get vtable and see if that works. That was here, I think. No, actually, let's try to do it with GDB, because I have a feeling that this one might be inlined as well. So target remote Raspberry Pi 333. So yeah, that's one of the benefits of debugging the code in the emulator. You can set as many breakpoints as you want. You don't have to worry about like number of FPB or whatever that would be. All right, so break rq.c at 102. It didn't say anything about the amount of locations. That's a good start. And let's continue. And breakpoint hit. Yep. So now we got it with the real Pi. And maybe we can just, call get vtable and see what it returns here. No, we can't do that. And I guess the reason might be because get vtable is inlined. Maybe if we delete the breakpoint, we can just write and then call it again, it will work. No, it seems like this is very unhappy about what we did. So let's try to restart it. Target monitor reset init. Add the breakpoint again. That was breaking here, and go back here. Okay, cool. It's so much faster when working against the real Pi. I wonder why the simulator is so slow. Anyway, layout source, so we can see the source code side by side. Actually, no, layout assembly, and then we can, or both of them, and then we can probably try to figure out where it reads this vtable value. So if we step one instruction at a time, so I loaded something R1. So what's in R1? It doesn't seem like a legit pointer. And then yeah, I don't know what I'm doing here. I think I'm not where I think I'm. Where am I? Maybe I already stepped over. Interesting. So I think what happens here is like the compiler rearranged the lines of code. So now we are like in a different function. Even though we set a breakpoint to go inside this function, it probably like went before this function. So I think the takeaway here is that we should try to get the code without all these debug optimizations, because otherwise debugging would be very painful. So let's see if we can set it somehow. I think I already compiled it in debug mode, but it may only set the symbols. Okay, let's see that. Yeah, but then we'd have to re-upload the program to the Pi. But let's see how to go about it. Build hello world debug version. I think I already did that. Like build it with build type debug. Maybe, just maybe, I'm not sure. No, if that was, I was thinking maybe I compiled it in debug mode, but I didn't upload that version into the Pico, and that could be true, but still the fact that it inlined IRQ get vtable handler, it seems like, let's see what this build type debug is doing. De-optimized sounds like good. Oh, there is another like variable, Pico de-optimized debug. So maybe we should set that. What's the default value of this? Yeah, I guess we should just create a de-optimized file, so we'll have easier time. 0, so I guess it's false by default. Cool. Let's try that. Let's try to recompile everything in the examples. Pico examples. And then we just need to do. Okay, so let's just take a note of that flag before I forget it. So it should be 1. And then we have this like export that we need. Then just CMaking to reconfigure everything. Okay, and let's cross fingers. Oh, we can just build one example. That would be faster than rebuilding the whole thing, I guess. So, configuring done. Now waiting for the configuration to finish. We will. There is nothing else we can do other than wait. Cool. So, configuring done. So it finished. So what are we waiting for? So now we are going to city into, you know what, let's do the UART, the allow UART, so that we have both, like the physical one and the simulated one run the same example. So that would be here. And we are still waiting for it. It says configuring done. Okay, so meanwhile, let me restart my Pi Pico into bootloader mode so we can upload the new code once we have it. And yeah, so this is like the drive for the Pi Pico, and I'm going to upload the firmware here as soon as this is done. It's really slow. I'm not sure if it should be that slow. Yeah, the thing is I have like WSL writing to Windows partition, so file operations are pretty slow, and I didn't plan to compile here. So meanwhile, yeah, let's clean up the tabs that we have. I think we can also, no, we need all of them, I think. Maybe, yeah, let's give them. Okay, let's see, is it still configuring? Oh gosh, yeah, that's why I like to pre-build everything in advance, but I guess I couldn't guess that we would need that. Anyway, let's go to the datasheet in the meanwhile and see if there is like I will tell you what I've seen about it. So while reading the datasheet this weekend, I noted a few interesting things that we can implement. So there is like this SAO block that lets us access some of the peripherals, and it controls the GPIO. So once we want Blink to actually work, we would need to implement that through the SAO. But if I'm not mistaken, where was that? there was something about the SIO that's yeah. Oh no, that was about the peripherals, I think. So processor subsystem. Yeah, there was something about it. Let's see if it's finished. Yeah, it's finished. So we'll go back to that in a few moments. All right. So yeah, I have the comments already. So let's build that. And that should be super fast because we are just building hello UART. And we'll need to copy the result back to the simulator and also to the Pi Pico. So we'll do that in a moment. All right, so we have the executable. Let's copy the result. I think we are working with hex files. Let's just see that it was. Why doesn't it show it on the sidebar? Okay. Hello UART.x. Let's see that it was updated. It seems like very now. And make sure we are opening the right one in VS Code and not the, I don't know, another version. Okay, and paste it to the simulator. No. Hello UART.hex. You have been updated. And now let's start GDB and see if we get a better debugging experience. So go back to the launch configuration and switch back to using hello UART and the simulator, the emulator of the Pico and F5. And where are we? Oh, I think we killed all the breakpoints. So oh no, we still have this one. Okay, so I think we stopped in the breakpoint, right? No, we stopped. It seems like we stopped inside this assert function, but unknown source. Why is that? Can't find the source code, even though I think we loaded the debugging symbols, right? This is like the ELF file. Yeah. Let's just double check that this is like the same file, even though it should be. Yeah, it seems to be the same file. So does know the call stack. So did it like not include the bug symbols, even though we spent all that time waiting for cmake build type equals debug? Yeah, I think it sounds legit. Yeah, I mean, I guess the best thing we can do is just to totally start over. Let's do that. Cd rf build. Okay, it makes me a little sad to do that because I know we'll have to wait all that time again, but then we might get a program which we can debug more easily, so it might be worth the pain. Now we can go back to the datasheet while this happens and look for those nodes I've seen in the weekend. So there is like this part about the peripherals. So there is, maybe it's here. Yep. So yeah, I think it was here, like there is like all this information about those memory buses and the mapping. Oh yeah, this part is interesting. Like so there is the APB bridge, which interfaces the high-speed HTTP light with the lower bandwidth peripherals, and if I'm not mistaken, all the UART and stuff they live inside this this like AHB light or APB bridge, and then there are like how much times it takes to access and so on. But then there is this interesting section. So memory mapped IO registers in the RP2040 ignore the width of bus read-write access. So it doesn't matter if you write like 8 bits or 32 bits. They treat all writes as though they were 32 bits in size. This means that software cannot use byte or half word to modify part of an IO register. Any write to an address where the will affect the content of the entire register. And then I think they have some examples here. So in this case, like they are writing a single byte, but you can see like the result is like copying this byte 4 times, and then same for writing 60-bit values. So I think that's something we should implement when we that was the AHB. So you see the APB bridge, that was the part we were reading about, and you can see like this access, like all the peripherals go to this APB bridge. So basically when we implement writes to any of those peripherals, we'll need to take care of this behavior where only 32 bytes 32-bit write are allowed. And right now, like, oh, it finished. So let's rebuild it. Yeah, they told us to remove the build directory, so maybe we should have followed the complete instructions. Cd build, and I know we did that, but just for the sake of completeness. And then we have this our own make command, cmake command, with this extra flag that I didn't know about last time. So let's run it, and it will take a bunch of time. And now we can go back to where we were. I think we were. Yeah, so yeah, when we get back to when we write to registers, right now we have like those helper methods that we have here, those write uint32. So if we write to 8 or 16-bit, like if we have a narrow write for 8 or 16 bits, then we'll read the value, just update the relevant bits and write the values. And that's not the correct behavior for this APB bridge that goes to all these peripherals that we have seen here somewhere. Yeah, to all those peripherals. So we'll need to update it to match this behavior. And in general, I think there is apparently a very big advantage to reading the datasheet end to end, but the disadvantage is that you remember a lot of facts, but then you can't remember where you read about them. But it's useful when you go to implement things. The other thing I read about is, I don't remember, from SRAM. Yeah. Is it still building? Yeah. So I'll keep entertaining us with the datasheet. So yeah, maybe it was here. There was like something that was, maybe it's in the address map. So yeah, there is the APB peripherals, which is like all the peripherals basically. And you can see, but I think they wrote it that like there is like a unique prefix for one of them, but then the lower 12 bits are always like peripheral specific, but I remember reading about it somewhere. Maybe. Oh, yeah, that's what I was looking for. So you can see like there are like the peripherals, and yeah, this is not interesting. This is interesting. So you can see like there is this peripherals, and it says each peripheral register blocks gets 4 KB of address space with registers accessed using one of 4 methods selected by the address decode. So apparently there is like, you can read or write from the address, but then if you add one of those values, like you said, is these 2 bits here, like the 2 least significant bits here, to 1, 2, or 3, the writes have a different effect. They don't like update the value, just override it. They either store bitmask set or bitmask clear, and that's something we should take care of it, because at some point we will have some code that uses that feature and suddenly something won't work. So this is something we are going to implement. I don't know if today, but pretty soon. I took a mental note that we need to do that. Now let's go back to the code and see what's going on. Let's rebuild this hello UART. Should be pretty fast because we are only building one project. Yeah, so that was like a little distraction while waiting for the compiler. 2 pieces of information that I discovered this weekend about the atomic register access and its narrow register IRO register writes, that we should take care of them at some point in the future. All right, let's see. It compiles. Hopefully now it compiles with the right options. I think it should print something about this being a debug build with no optimizations, but I don't see anything like that. So are we optimistic? It's finished, so let's just do this. I think it was smaller last time, right? We have a copy here on the hello. Yeah, it seems to have grown a bit, so this might be a good indication that we actually managed to turn the optimizations off. Let's try that. Start GDB and then run GDB from here, like the client, and see what's going on. What is that? Okay. What happens? We are running stuff and we have like a lot of invalid memory address reads. Let's pause this and see what happens. Oh, something went really wrong when we turned off the optimizations. Maybe we will try with the standard GDB. That would be faster. Remote winhost 333. Target remote. Let's just restart it. So we use it with the correct ELF file. So that was hello UART, then file hello UART.elf target remote. Huh? That doesn't sound very good. This Drawf Error. Maybe we are using an older version of GDB multi-arc. So dwarf is like the debugging symbol. So if it can't read those, it means that we want to go to winhost. It means that we may not have the best debugging experience. Let's restart that and redirect the output to a file so it doesn't flood the console. Okay, and now we can hopefully No, it brings this to the stderr. Okay, at least we got GDB to connect to this, and now let's break in. What was that? This function. Let's be optimistic and see if this one will work. I mean, it should be now de-optimized, so it should be a simple function. We have all those read from invalid memory address, so maybe we never get to that point. Let's try to pause the execution. Do we even support pausing the execution? Yeah, I think so, but maybe we... Okay, let's try this on the actual Pi, see what happens. Yeah, to get this file, so Pico examples, build hello UART, no UART hello UART. Okay, so we have this folder, and now we can upload this into the Pico, update the code. Now let's see if we are able to debug it at a Pico. Okay, launch.json. All right, so we want the hello UART. We just want to debug the Pico this time, not our emulator. And F5, will that work? Let's look at the... Oh, it's running, cool. And if we pause, let's see, where are we? Exit, breakpoint, signal handler called platform entry, unknown source. Yeah, I'm not very optimistic. Let's try that with GDB for a moment. Target remote Raspberry Pi 333. Oh, that doesn't seem like a good place for the Pi the code to be at. So target reset init, right? Monitor reset init. Okay. Breakpoint at we already have the breakpoint, right? Info break. Yep. Okay, so at least on the real hardware, we finally hit this breakpoint. So it means, but for some reason it doesn't link with the source code. Interesting. So I don't know, something is wrong with the ELF file. I will have to figure that out. Which is pretty annoying because now it's much harder to debug, but we can at least run finish and see what the function returned, or maybe not. Yeah, I think the return value is probably so yeah, now that this assembly is much easier to follow, so I guess the return value is inside R0, because that's the next thing it's doing. It's reading from R0, and we can see, yeah, this is like the address of vtable, which is what's this address, and then. Okay, let's first of all write this down somewhere. Let's do it here. So get vtable on real Pi returns, probably it returns this value, and then all right, then we have this was in rq.c. So then we have this index. So we add 16 plus num to the and use that as the index into the V table. So we expect it to read at some point here, probably this second LDR, I guess. It should probably read from this address plus, I think num was 3, if I'm not mistaken. How can we know that? It was probably passed in R0 or another variable. Frame 2. R1 or R0, one of them. Hardware alarm cancel. But oh yeah, right. So either R0 or R3. Yeah, I think we are in the same place like we were last time. So probably it's still 3. If we look at the registers, we can probably see one of them containing this value, or maybe not. Don't see any 3 here. Okay, let's keep going with the registers and see with the instructions and see what happens. So LDR3, R3. Okay, so it loaded it probably from the stack or something like that, but it's probably this num, because now we are adding 16. So R3, so that's 19, and then we are shifting it left by 2, because this is like returning a pointer. So array index is multiplied by the size of the pointer. So that's 4. So that's why we shift it left by 2. And then we have like 76, which is apparently 19 times 4. And then we are adding that into the value that we cut before. And yeah, and then we can yeah, and then we have the so the result was turned into R3. So this is where we are reading from. We are reading from this location, and in our code it returns FFFF, which is -1. Let's see what it returns. Let's write it down before we forget. So this is the function IRQ get vtable handler. You get vtable handler 3, return reads from here and returns yeah, that would be the LDR. That would tell us what it read from it. It returns this value. So this is like the, and I think I recognize this value. This was the the default handler that we have seen before. Turns this. Okay, cool. So this is on the real Pi, and then we can compare it with what we get, but we can already see something that might give us a hint at the problem, like this address. What's there? This 2000 whatever. And I have a feeling that I know the answer. If you remember, or maybe I don't. Well, let's look at the datasheet. What's there? So that's the SRAM, right? And that's like the beginning of the SRAM, and something should have okay, let's check the code, but something should have put that address there at some point. If yeah, if just in case we actually get this this one correct, like if vtable, and we'll verify that in a moment in the simulator, if vtable still returns the same value. Okay, so let's go to debugging the simulator, and I don't know what is all this invalid memory address. Let's see what's there. So this is like the SAO base, and that was the 1 to 12C. So what's a 12C? 12C. Spinlock. Interesting. It's probably trying to acquire a spinlock. And this will return 0 if the address is already locked, or non-zero and simultaneously claim the lock. So what do we return? In this case, read from invalid memory address should probably return all F, so it should probably work. Invalid memory address. Yeah, in this case we return all F, so I think if it's trying to acquire that spin lock, then it should return non-zero, and yeah, but it doesn't work. Anyway, let's try that again. Maybe we'll get more lucky at understanding what's going on. So start GDB, and then let's target remote localhost, no, in-host to connect to the emulator, debugging win-host at the beginning, cool. And then let's just continue, I guess, and try to break. Yeah, I guess all those prints just mess up with the terminal, so let's just disable this for a moment. And did we get lucky? No. Okay, now we don't need to get rid of the output. Okay, and let's retry this debugging. Win-host 333. Cool. Continue. And what is CPSADI? Okay, I still can't break for some interesting reason. Read, write to undefined register. Okay. Yeah, I wonder why. Is there like a bug in the gdbserver? There is like this. Oh, interesting. So yeah, so if we are getting we should be bringing a break when we get like this interrupt request, but we are not actually breaking. I see. We just print break, but we don't break. So let's implement that. So basically, if there is like a break request by hitting Ctrl+C, then we should probably just call this method, or maybe just rt2040.stop, and then send GDB. I think we should send it a different message. If I'm not mistaken, we should send it. We had this signals. Yep. I think we should send it SIGINT in this case, which is number 2, because it was interrupted. We didn't hit a breakpoint. So stop SIGINT. SIGINT, yep. Stop reply SIGINT. So that would be 02, and then where was that? It was down below. Okay, and then we can send GDB stop reply SIGINT, and maybe that would make it possible to pause the program at any point with GDB. Let's try that now. Okay, so this is the program, this is DDB, target remote Windows 333. Let's doing a bunch of stuff. Continue. Okay, now, no, it doesn't seem to want to break. It's not getting this break, is it? Why don't we, let's just read everything that we get here and see what's going on. Okay, target remote win host 333. All right, continue. Then do control break, control C, but this is not getting anything interesting. Like the last input that we got was just this buffer that probably told it to continue. But then when I try to break, it doesn't get anything from the socket. So it becomes non-responsive. Oh, I know why it becomes non-responsive. I guess I know. So I think it has to do, we can remove this console log. I think it has to do with the way, yeah, we implemented execute as a busy loop that just runs forever, basically, until stopped equals false. But since JavaScript is an asynchronous language, if we are stuck in this while loop, then no other events would run and we wouldn't be able to get to this listener, because nobody is going to look at the socket and see that there is new data available, because the main thread is busy running this code. So the thing we are going to do here, we are going to change the code a little and use a counter here to just, you know, I0 I less than, I don't know, just arbitrary number, maybe even smaller for now, and we are just going to yield after a while just to return to the JavaScript event loop. So as long as these and not stopped, we are going to execute an instruction, and then once we are done, we can just set timeout. This does execute, so run ourselves again within let's say 0, basically immediately, but that would yield to the event loop and let JavaScript process the messages coming from the sockets. And let's also create a variable that will allow stop to cancel this timer, because otherwise it would go back to execute sets stop to false, and even if somebody asked to stop, it would still keep running. So let's have another variable that would let's call it private execute timer equals null, and then this dot execute timer equals that. And yeah, we need to say that the type of it is either timeout or null. Where does timeout come from? Node.js.timeout, okay. Node.js.timeout, cool. And then here, if this dot execute timer is not null, then clear timeout, just kill this timer, this dot execute timer, and set this dot execute timer to null. And now the execute loop should yield every 1000 instructions, and hopefully it won't get stuck like it did until now. Let's see it. Target remote Windows 333 remote, cool. Continue, invalid remote reply. Okay, interesting. And now it does get a break, but I think something with the invalid remote reply confused it. So let's disable the text user interface, clear the screen, and then target remote winhost 333. Okay, first of all, we can already see where we hang in this in this place, why is it so slow? Maybe all those reads. Yeah, now we can see it's still like in the hardware alarm claim, but probably earlier we have like some issue. And yeah, I wanted to do target debug, set debug remote 1 to see what's going on, why it gets an invalid reply. Okay, it sends vcont and then it sends another vcont, and I guess it doesn't expect an empty packet here. So why do we send it an empty packet? And I guess the reason it didn't happen before is that before, when we had this where is this execute, when we have seen this vcont, we just yeah, that's our reply. So we have seen this vcont and we just called execute, and execute blocked forever basically until we hit the breakpoint. So it never saw that reply, but now we are execute doesn't block, it eventually returns, it yields and continues the execution. So now we have like this empty response, which is not supposed to return from cont. So in this case, we can fix it by just telling, just returning. So we don't get to that line here at the end of the function where it returns an empty response. So let's try that again. Target remote winhost 333, whatever. See continue without paging. Okay, cool. And then see, and we see that it doesn't complain that there is like a problem. And if we control C, it seems, let's just debug remote 0, where yeah, we can see that it works. We can like continue, and we should remove those those prints. They are probably slowing us down, but we can continue and we can break, and it works. So another feature to our debugger, we can finally break while the program is running. Yeah, so this one. We also need this change to the execute loop. Let's see what we did here. So we added this. Oh, don't want to debug my tests right now. Okay, yeah. So we added this execute timer. We don't want to commit that right now. This change is not to be committed right now, so let's remove it. Okay, so execute timer, and yeah, it looks legit. So gdbserver allow breaking, interrupting while, or maybe allow breaking with Control C from GDB. Cool. And second commit for today, second feature for the GDB server. And yeah, and now we can finally break. I'm still concerned about the fact we can't see the source code. Like, why did that happen? We have the sources in our system, and there was that note about Drawf, and I think it might have something to do with it. File that was allow.ur.elf. Let's try to Google that and see if there is something that helps with that. Because it will slow us down if we don't find go away. I don't want to accept all cookies, whatever. One of your update GDB to compile using another work. Okay, I didn't know it's choosing the right GDB version. So Should I update GDB? Is that a thing? Let's see if I can. GDB multi-arc. Oh, I need to update first to get a new index, and then I can try to see if there is a new version, but I guess there won't be. Yeah, it's already the latest version. Maybe there is something about it. I mean, they told me to use GDB multi-arc, so maybe there is something, because it worked before, so maybe it has to do with some of the recent changes they had. Let's git log and see if there is anything interesting. So merge 5, not relevant. Pico examples, git log. Yeah, I haven't updated this for a while, so the code hasn't changed. So maybe something on my system has, but I don't know. Maybe let's try to Google that specific error with Raspberry Pi Pico. Yeah, I don't think there is anything useful here. And the other interesting thing, like here they have like, now it's like 4 or 2, but we have like version that doesn't make a lot of sense. It's like a few thousand. Or was that? It was here. It was like version. Where is that? Version. Oh. Yeah. This doesn't make sense. I mean, I would expect to see 6 or 7. It seems like a problem with something in the build process. So I think what I'm going to do is just let me try to just run this inside, to rebuild everything inside this local directory that is local to WSL. It's not like a Windows map directory. That might help a little. GitHub Pico SDK. So let's clone this Pico SDK here. And there is also the Pico examples. And let's go real quick on the Pico setup. Oh, they have like okay, Pico SDK, git clone, git submodule init. We need to do that. cd Pico SDK, git submodule init. That will probably take a moment. And then we have cloned the Pico examples as well. Yes, we did. We are pretty fast. Okay, and then we just need to run the build again and hope for the best this time. So that was here. cd Pico examples, mkdir build, right? And then cd build. Exporting this, and yeah, we have our own make command, and that's a super clean build. So maybe that will work better. cmake, and maybe it will also be faster now. Yeah, wow, that's so much faster. I'm not going to keep using the Windows mapped drive because this is so much faster. Okay, so cd uart hello world hello uart, and then we can just compile here. That was yeah, just make. Okay, paste anyway. Okay, cool. Wow, that was also so much faster. Okay, and now I would love to assume that we have the same file, but that wouldn't probably be the case. Let's open this with Visual Studio Code just to copy the contents of the file. Okay, so copying this hex file to the emulator. That was low UART. Maybe it was the same file, I don't know. Anyway, let's restart this thing with the GDB, and now let's try to run GDB from here. So GDB multi-arc, and use this help file, elf file, this one. Oh, no warning about bad symbol Drawf version. That's good. Windows 333, and it should connect now and continue, and now we should break, and hopefully, yep, yeah, we can see the source code. So now we can just use this elf file inside VS Code and get proper debugging. Right, so it was in the launch JSON, and this elf file is now the relevant one, and we want to connect to the emulator. Let's try that, and super better debugging coming in a moment. Where are we? We are just running. Let's pause. Yeah, I should remove all those reading from. I think it really slows down everything. Yeah, where is that? It's inside gdbserver, so we don't want that to go away. And yeah, that now this will die because we restarted the process. So I will just continue and restart the debugging session. Okay. Now we can pause, and hopefully that would be a little bit faster to pause than it was before. Or not so. Anyway, yeah, we can now see what's going on. We have like this alarm claim, alarm pull init, unsafe blocking. It just built-in expect. So it's running from this address, and it expects it to be 0. Oh, it expects not this. So it expects it to be, I guess, what does this do? Built-in expect. Probably nothing too interesting. Isn't it defined anywhere? Maybe, no, not sure, but probably it should just wait. Let's see what's here. Let's just printing in the debug console. So Valeria is asking in the chat if the optimized debug changed the game. Not sure which game it should have changed, but let's print it as, I'm not sure, exec print. Yeah, it seems to be reading all F, so I'm not sure why. I mean, this should be 0. Oh, I think it waits for this to be 0. Let's read the docs. So I'm not sure what Valeria was asking about, but basically now we should be able to debug, like, to put breakpoints, like we did with the actual Pi GDB inside any function, because the compiler won't inline them and won't change the order of statement and do all that kind of stuff that makes debugging harder. Requires spinlock without disabling interrupt. So it expects this I think it expects it waits for it to get 0 because I think the thing is, like with those locks that we have seen, what was that? It was here. It was inside. So it expected to return 0 if the lock is already locked. So probably this code just assumes that it will first return non-zero and then return 0 because this will be locked. So it wants to see that it has been locked. Anyway, so what we can do for now, we can cheat our way for now, but eventually we'll have to implement those locks. Let's go to RP2040 and then we can say, let's see. All right. We have the constructor where we put all this bunch of like locks, this .read hooks .set, and that was SAO spinlock something. What was the address of the spinlock it was reading from? Lock 123C. 123C. So that's spinlock. I think there was like the list here. 123C. Spinlock 12. No, spinlock 11. Yeah, so spinlock. I think we already have like the SAO base. Maybe, yeah, SAO start address. So const SAO spinlock is 12C. So if we are in the, just double checking the address, D0012C. Okay, so if we are reading from SAO plus SAO spinlock 0, then we just want to return 0. Do implement spinlock mechanism. Cool. Let's see if that saved the day. We restarted GDB, so let's restart our we restarted GDB server. So let's restart our debug session and let's see. Oh, that seems like it's trying to lock another spinlock. Where are we now? Debugging. Yeah, I wonder why this didn't happen in the optimized compiler, but yeah, we can see it's like doing here, canceling some alarm. Yeah, that was like the previous time. Now we have this place where we are like getting confused with those spinlocks. Anyway, let's do that. So that was Valeria asking if after enabling the optimized debug it stopped working. So yeah, I think it changed the game with these spinlocks. I'm not sure what happened with these debugging symbols. Probably something that has to do with times of files or God knows what, because of you know, like the files were sitting on a Windows file system and I was like building on Linux. I have no idea, but now everything is in the Linux file system, and as you've seen, like the builds go much faster, so there is no reason to keep the stuff on the Windows file system, so we'll stop doing that. Cool, so we have this second lock, exec/xlock, which is at this address 128, so it's just like the previous one that was yeah, so that was actually not 0. I think that was spinlock 11 there, right? 1, 2, C is 11, no, 1, 2, C, 11, and then 10. So this is 10, this is 11, and spinlock 10 and 11, they both should return 0, just so we get past this point. Now we can have 5, and oh, we need to restart this because the gdbserver restarted. And hey, gem, AB2, hey. Okay, so now we have another one, I guess. Oh, wait, what is that? Did we stop at a breakpoint? Interesting. So we had something with reading from. Is it like still printing stuff, but GDB thinks we are stopped? Okay, interesting. That's strange. Seems like we stopped and never stopped at the same time. Anyway, let's see, where have we stopped? And num here doesn't make a lot of sense. Are we looking at the wrong ELF file or something like that? Something is really fishy here. Let's just step. See what happens. Yeah, I don't know what happened, but it doesn't seem correct. Anyway, let's implement just all the spinlocks, because I think otherwise we'll just trip on them one by one. So I think the first one is at 100, and then there are like 32 of them, right? So the spinlock 0 is at 100, and const, not Hebrew, const sao spinlock count is 32, and then we can just for let I 32 I plus, and we can so Jam is asking, how is it possible that I remember all of it? So the answer is that I usually forget things, and then I guess every single one of us forget different things, and that's why I really like to have people on the chat here, and hopefully sometimes they catch stuff that I don't. So I think everyone has like a kind of buffer in their brain, and then oh, this is return 0, and then they just fill the buffer with different kind of information. Maybe let's change it from I to spinlock index. Okay, so maybe now it will go past all those spinlocks. But it's just a theory. Okay, now we are somewhere else. Let's pause and see where we are. Pausing doesn't work now. Let's restart a debugging session. Even stopping doesn't work. Let's restart everything and see what's going on. All right, 5. Okay, let's try to pause. Yeah, it doesn't seem to be breaking. Let's try it with the real GDB, the actual GDB. Let's see if that works any better. Oh, file load ur.elf remote winhost 333. Continue. Now we have this bunch of stuff going on, and we broke. Yeah, it worked here. Where are we? How did we get to that nonsense memory address? Oh, but we do have a stack trace though. We are inside vs and printf. Yeah, okay, so it seems like here since we enabled debug information, maybe we have I don't know why we die here, but we are at the same place, like in this IRQ set exclusive handler. So it seems pretty promising. We got to the same location, but now maybe because we have more debugging info, it goes to VSN printf inside assert. I don't know, but we can see that the call stack trace, the stack trace makes sense, and we still stop at the same assertion. So, and we can probably see the sources here, frame 5, for instance. Yep. So it's maybe not this super fancy debugging, but it's still good. Let's restart it and set a breakpoint in the that function that we think is the culprit. So target remote winhouse 333, just reconnect. Target focus on the command window so I can use the history. Okay, we are at the beginning, cool. And I wanted to break. Okay, I wanted to break, that was IRQ, I think it was at the beginning in this get vtable function. Okay, break get vtable, continue, and will it hit a breakpoint? No, it doesn't seem to have hit the breakpoint. But when something fishy is going on, it seems like, let me see, it seems like I think I know what's going on. So we did a last change where okay, so we did the last change where we changed maybe I don't know what's going on. We changed execute, so now it sets up this timer, and stop is supposed to cancel this timer. And what happens when we hit a breakpoint? When we hit a breakpoint, it's here, we call stop. So I think for some reason this is not working correctly. Somehow, yeah, okay, I get what happens here. So when we hit a breakpoint, it's inside execute instruction. One of the instructions is the breakpoint instructions, and at that point it would call this callback and it would call stop. So stop would look at the timer and it would see there is like an all timer or there is no timer. It would call clear timeout, whatever. But then when we finish this loop, it also sets stop to true. So the next time execute instruction returns after executing this on break method, it will see that this stop is false. It will stop the loop, but then it will set up a new timer. So it will keep running even though we hit the breakpoint. And that's what we are seeing. That was also the weird behavior we have seen in Visual Studio Code, where it would just keep running even though it seems to have hit the breakpoint. So in this case, we can just do this check. If not this dot stopped, then and just for the good measures, if this stop is called from within execute instruction, it will try to kill this timer, which we set here, but it's like already void once this function is started. So let's just clear it here, because we know that if somebody called this function, this timer is expired, and there might be a better way to implement that. Yeah, actually there is a better way to implement that. We can just change it to an async function, and then we can probably get rid of the timer, right? We can just while not this dot stopped, so we can move this here, and we can just await new promise. That's a really fancy way that resolve set timeout resolve 0. This is just a really fancy way to make JavaScript will yield the execution without using a timer, or it uses a timer behind the scenes, but it hides this thing. But then let me see what happens. Yeah, I think there might be a race condition here if yeah, let's go back to the old implementation. I think it's less magical. It's a bit more code, but it's less magical. Cool. So hopefully now it will work. And hi Lars, good to see you here. I didn't know you were following this live stream, so it's good to see you here. Anyway, yeah, okay, so we got this bug probably fixed. Let's try again, target remote, and we have this breakpoint set, right? Okay, and continue. Connecting. Okay, continuing, and now it's stopped at the breakpoint without continuing to run. So cool, let's commit that. Fix gdbserver. What did we change in gdbserver itself? Oh, we removed this debug print, but we can probably keep it in the commit. Yeah, so so yeah, we are actually adding 2 changes at once, so I don't like that. Let's just I guess there is a better way to do it, but the way I usually do it when I have like 2 changes like this is just to delete. I think there is a way to tell Git just to stage specific lines, but the way I usually do it, I just delete the lines that I don't want to commit, and then I only have those lines that I do want to commit. Then I stage it, and then I just undo the deletions. But if you know a better way, let me know, because it sounds to me like there should be a better way. What did I just do here? Why is it called soy count and not SAO? Okay, let's fix that as well, and we don't use it. Spinlock. Yeah, I don't know why I've defined this constant but didn't use it. Anyway, so so this is like the first commit, fixing gdbserver breakpoint didn't really work. The program kept running despite having to stop on a breakpoint. Cool. And then let's save it so it's happy. And yeah, just those new changes in execute. Cool. And then the next thing we want to do, just RP2040 add spinlocks. We don't even need to add fit, means we added something new. Cool. So 2 commits in 1 minute. Cool. Okay, back to debugging. Okay, so now we change the code, so this will restart. Yes, and yes, and continue. And now we should finally be able to tell what's wrong with getVtable. I mean, we know what it's supposed to return. Now we can probably print this, or so I thought. I think there is such a symbol. I'm pretty sure. But let's try finish. And no, it didn't do the trick. Running finish. Interesting. Let's switch to assembly. Oh, what happened here? Okay, we got to assembly. So where are we? Okay. Invalid remote reply. Okay, interesting. Anyway, it seems like things are going here. So I think it's just like before. It's going to return the answer in R0. And yeah, that doesn't seem like the same thing we got from the Pi Pico. So I wonder why. So this explains why we get garbage. It should, I mean, scphw. Why doesn't it like show me the value of this global? I think. Okay. But yeah, we can like see. Oh, let's see where we read this value from. Yeah, let's just. Oh, we read from VTOR. So I guess reading from VTOR means RB2040 VTOR. So I guess reading from VTOR means this is like getting this value from this VTOR. But did we write any? Where did we initialize? We read from VTOR. And then reading from this address that seems to be very similar to this. So I think something should have initialized that value, but it didn't happen correctly. Like we have this thing. Let's just try to breakpoint here. Is this on break? One argument, whatever. This doesn't break, 0. Cool. And now let's see who writes there. So how we get that strange address: target remote localhost 333 whatever. Oh, it's not localhost, it's winhost. Okay, target remote winhost 333. Okay, continue. And right, yep, in flash binary start, somebody is writing to R0, which is probably, oh, it's writing R0, this value, into, so writing to VTOR. Wonder why we got 2 more writes here. Maybe that's GDB doing those writes. Yeah, it seems like flash addresses. So R1, so wait a moment. I think it's writing the, instead of writing like this value, it's writing the address. So there might be something wrong with the right hook system, because let's print the value. We are a new value. Okay, now we can just reconnect. And now let's see. Yeah, it seems like the code says like we stopped on this instruction, which should have stored a value of R0, which is this, but we got this value. So there is probably something wrong with this right hook system. Probably a bug here. Let's see where we call the right hooks. Hook address and value. Interesting. So the hook get address and value. So it's not a bug in the hook system, but how we used it. We didn't use it correctly. Right hook. Yeah, and so Yeah, we also did the same mistake here. I think so. We may have changed it because this probably worked, I guess, at some point. Or maybe, sure. Anyway, so this should get address and value, and now it will probably work correctly. Let's see. Okay, so reconnect, continue. Hey Lars, yeah, it's a bit far from the usual, even though you see I'm using TypeScript there and JavaScript, and I have to worry about that as well, in addition to flipping the bits. Anyway, so now it seems like we are writing the correct value, and I will take a wild guess that we should also fix it here, because, I mean, there is no way we wanted to check the address here. We wanted to check the value. We know like the address is never gonna be equal to 5, so it's probably another bug. Let's just see what's going on here. Continue. Okay, let's just see that we haven't totally destroyed anything. Okay, this actually destroyed it. Interesting. So maybe there is a bug here, because maybe we didn't get into that if before, but for now on, let's just add it to do here. Probably a nasty bug, nasty bug hiding below. Okay, but we don't want to fix it now. Okay, continue, and now we can see that it writes a value that makes sense to Victor, and then we thank you, Lars, and then we continue again, and we can see another write to this VTOR. Continue. Oh, it just, oh, I see. Yeah. Probably the breakpoint we have set causes it to just get stuck on the same instruction, because GDB retries the same instruction. Anyway, I think we found and fixed the bug, so we no longer need this breakpoint here. Target remote localhost winhost 333. Okay, continue, and let's see where we stop now. So let's see, get step table. It's next. I'm optimistic that now we get the correct result from it. R0, 3. Okay, interesting. Oh, R3. It's, let's step over one more instruction, so we have the result in R0. Yeah, okay, this seems good, because I remember that the we had it somewhere in some hidden window. Yeah, the Raspberry Pi, the real hardware, also returned the same value. Cool. And then let's just next to return from this function, or I don't know what happens now. Where are we? Yeah, we are in this get vtable handler, and let's see what it returns. Single instruction. So now this is like the outro of the function probably, and the result is already in R0. And yeah, it returned the value that the Pi0 returned. So I think we're good to go. Let's continue and see. Yeah, let's delete this breakpoint. Let's continue and see where we get, if we get anywhere. Where we get stuck now. So now, ooh, interesting. Now we got into the UART. That starts to be interesting. So right now we are where are we? UART get HW. All right, UART get index. I don't see any reason why this wouldn't work. Let's finish this function. For some reason, finish doesn't work correctly. Oh, it just did. I think finish. we're probably stuck in another loop, but inline UART is writable. Yeah, I think this should be good. Next. Or maybe not. Where are we? Next. Yeah, I wish this was fast. I don't know why it is so slow. We'll have to figure it out. Anyway, there is like UART write blocking, and let's see where are we? Anyway, I think we are in a very good position. Like we got back into main, so I think it's trying to print characters. So it seems like we are very close to hitting the goal of there is something strange here, because there is probably something that we are missing, but we got like past the initialization code, and now we are very close to getting output from this, like to getting this program to run from the beginning to end. Okay, so let's see. UART is writable. Let's switch to source only layout. So we are going to next. I think that it's probably stuck here, like determining if UART is writable, reading from some register and seeing if while not UART is writable. Yeah, I think we had this in the past. Let's see if we have like anything for this UART. UARTR, UARTFR. Let's go to Visual Studio Code. UART is writable. Huh? Oh, that's in the boot ROM. That's not the interesting one. Interesting one is the SDK. So yeah, this one. So it reads from TXFF. So what is this FR? Let's go to the datasheet to see what is this FR of the UART. UART, list of registers, UARTFR, flag register. And we don't have it yet, probably in the code anywhere, right? We have like this UART. Oh, we do have UARTFR, and then we always return 0 for UARTFR. And which flag are we looking at right now? It was this one, TXFF, like this. And it's writable only if this flag is not set, right? And it's probably not set because our code says it doesn't, because it's just 0. Let's just double check this. TXFF. What does datasheet say? Full. And yeah, it's not full, so it can send. Interesting. So for some reason, it seems like it's not doing this. That the UART is not installed. And I think the reason is we haven't. Oh, that's stupid. We have probably not set up the UART inside the GDB stub, and I think it's pretty stupid to, sorry about that, but it's pretty stupid to initialize it here. It should probably just be a part of the RP2040. So because we would want read only UART equals new ERP UART. With this, we would want simulation without UART. I mean, I wouldn't. Yeah, it seems to error. RP UART. So yeah, so it's my bad that I didn't include a UART here by default. And now we can probably say mcu.ur.byte, and let's also set this up on the gdbserver. So where is so just rb2040.ur.onByte. Okay, rb2040.ur.onByte value. Okay. Okay, cool. And now hopefully the program should run. Let's try that. WinHost. Yep, continue. Where are we? Why don't we get any output? Where? What did I miss this time? It seems like in the same place UART is writable. Reading from this value that. What is this? Anyway, now we should. Did I forget to save some file or something like that? Anyway, before, let's just commit the previous fix before we go to this. So I'll do the same trick again, where I remove the lines that I don't want to commit and just commit the fix. And I think we can also remove those debug logs. Cool. Invalid value in VTOR register. Okay, so that fixes that issue that we had. Cool. And now we can add the UART again and try to figure out why it doesn't work. And let's remove those read console logs again. Cool. So now we should only have the UART. And let's add some debugging code here to see what's going on, like to see if this read is actually intercepted. That's UART FR. Okay. Okay, target remote Windows 323. Continue. Yeah, there is like it's reading from there, and it should return 0. But for some reason it doesn't. Which UART are we using? 3400, and I think, oh, there are like 2 of them. So what are you doing with those base addresses? Oh, we only attached 1 UART, okay, but it's the same UART that it's writing to, so it's fine. Okay, and now finish. Go back to the parent, to the color, finish. So now let's try to print the value of this expression. It should be true. It doesn't like this, but I guess this is just 1 shifted by, this is bit number 5, and this is 1. It's reading it, so this should return true, right? Let's go back to the color, and it says that the return value is false. Interesting. That's super interesting. Let's break at UART is writable and see how comes it says the return value is false, even though we saw in our eyes that this evaluates to 1, which is truly truthy. Okay, we stopped here. UART is writable, layout split to see the assembly code. And now we can step next instruction, step instruction, skip instruction, just get the value of UART, get HR. Actually, it doesn't matter if we step or next here. Okay, so this is probably going to read now this LDR from that register UART blah 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 arrow FR. We'll see the console for that. Yeah, we can see it read from that register, and it has the value 0. And then maybe we have some bug in one of those instructions. Let's see. So we move 32 into R2, but yeah, R2 gets 22, and then we end R3 with R2, so we expect the result to be 0, 0, good, and then we negate the value of R3, so we expect that to be all Fs. Ooh, interesting. Oh, right, neg is like NEGS. What does NEGS do? Maybe that's okay. 0 is negative 0. Is it like just where is NEGS? Where is the instruction set? Neg. RSB immediate. Okay, maybe that's good. Not sure. Let's take a look at the tests for neg. NEGS. Yeah, it's just negating this value, so I think that should be fine. -0 is still 0. It's not bitwise. Not okay. And then we are adding CS, R3, and R2, and we know that 0 and 0. And what does CS do? ADCS. Add with carry. Why should we have a carry? Maybe from the next, but it was all 0, so it should probably be 0. Okay. And then we have this UXTB, which should still be 0. And then we are returning 0. Interesting. So something in here doesn't work as it should. Well, one of the instruction is definitely wrong, because this should have returned 1. I wonder which one. UXTB is like sign extend, right? Unsigned extends 8-bit, 0 extends from a register. Okay, something is definitely wrong here in the logic, but the question is what? I think NEGS isn't doing, or one of those two, like these two are probably not doing what they are supposed to do. Let's Google it real quick. Maybe NEGS. Neg, okay. It's RSBS. Reverse subtracts register from immediate. Maybe this doesn't update the carry correctly. Right, so it's interesting that we implemented that opcode, even though it's like just RSBS, but we haven't implemented RSBS. Okay. Let's take a look at the test cases. RSBS, no, next. No, this is not the test case. Next. Okay, interesting. We just call it here RSBS, and here we call it next, but it's probably the same thing. Yep. And I think we either got the carry wrong or the result wrong, and I think yeah, we probably got a carry wrong because 0 minus 0 is, oh right, it's Rn minus 0 if I get it correctly. Thanks, Lars. Yeah, it's pretty wild. I'm amazed by this every week. Okay, so I'm subtracting 0 from 0, so the result is obviously 0, and then I'm putting the result into R2. So this is 0 because this is the end of those. I'm putting the result of this. So I think there should be a carry. The problem seems to be with the carry. What does add with carry do here? Turns result, carry overflow. Not Rn, and IMM32 is probably 0, yeah? Oh, wait a second. Wait a second. It's adding not Rn. Oh, with carry. So not Rn is all Fs. That would be, and then I'm adding 0 and 1 as the carry. So it's 0. But yeah, there is a carry here, right? Because we added all Fs plus 1. So it's zeroed, but we had carry. So then I think that's the problem, the carry flag. And so let's make another test case for that. So basically, if we add 0 here, right? The result would be 0, which is what we observe. But let's remove this from filter. But then it's not negative. But then carry should be true. It's not 0. Oh, it is 0. But then carry should be true, but it isn't. So we found this. And I think this is the only case where the result would overflow. So basically, yeah, we had here a problem. We thought when we wrote this that carry would be true if the result is -1, because we thought that adding, yeah, actually, if it's -1, then the node of it is 0, and we are adding 1 to 0, which would not have carry. So yeah, it should be if value is 0, it would have carry. Okay, I think we nailed that down. Let's commit that. Oh, we still have that UART bit. So let's again do the same trick. We will just revert this and just add commit this. We don't need all those console logs anymore. We want, wait a second, let's just clean up. We don't need this. Let's just clean up the workspace a little before doing all those changes. Okay, so we changed UART. We don't need this anymore. We can just revert UART. We don't need this change. It was just for debugging. And then in run blink, we said we don't need all these console logs. We don't even need this, I think, but let's keep it just to keep the history clean for now. So we don't need the UART. And then in the gdbserver, we added the UART. fit UART or fit RP2040, always initialize UART. And you know what, let's even do it a bit more comprehensive. We know there are like 2 UARTs, so let's make it an array that has already these 2 UARTs, because we know there are like 2 of them, so why be lazy and just initialize one. So there is like UART 0, UART 0, and UART 1 base. Cool. So yeah, so now we need to change the code. So it listens on UART 0, and here as well it listens on UART 0. And that was here and here. Maybe I would say fit UART because it's related to UART, and always initialize UART 0 seq1, comma 1. Also add a UART to gdbserver. Output support to gdbserver. Cool. All right, we can commit that, and then we can commit the other bug fix that we had, where we changed this. Yeah, we had this RP2040. That was NEGS. We changed this to 0 and hopefully fix that issue that we had here. Okay, and let's also say that this is NEGS also, how does it called, RSBS. It's the same. So next time when we search for that instruction here, we'll find this. Okay, cool. Fix RP2040 bug in next instruction. And now just before, not next. Okay, now just before I commit, let's just run it and see if it did a trick, if we get a program to run finally. Okay, target remote winhost 333. Yes, target remote. Continue. And no output. Interesting. Where are we? Again in the spinlock thing? Hardware. What happens with those spinlocks? Did I remove that code by mistake? There was like this spinlock. Ooh, but it worked before. Interesting. 34 minutes ago we added those spinlocks. Anyway, let's print the value of flock 1 to C. Let's add a console log reading from, I guess this also gets the address. Right, maybe, no, this seems it. Okay, let's retry that. Yeah, it's reading and it returns 0. Oh, now I get it. I think I get it now. So we didn't need that. Like the code was checking if the spinlock is 1, but because of the bug that we had in NEGS, it had the logic inverted. So we don't need all of that right now. We can probably remove it. So it's like we hit that because of the bug with NEGS probably. Let's just remove it and see if this works now. Okay, continue. And what happened here? Where are we? Did we get any kind of things that looks like serial output? Not yet. Oh, yeah, we have the breakpoint. Let's be optimistic and just delete it and see what happens. If we get delete, there is another breakpoint. No. Yes, I think we have output from the UART. Cool. I think we did it. I think we managed to run a low UART beginning to end. Let's just remove all those debug logs so we can actually see that if we did it. Where is all this reading from? And someone wrote reading from. Where are you? Don't want you. Go away, go away. And then there is like this, someone wrote, okay, yes, oh, and target remote. And I think that breakpoint that we had hit is just like the end of the program or something like that. Let's try that, continue, GDB connected, GDB disconnected, GDB spam, continue. Yes, you can see it loud and clear. Hey, AB, hello, UART. So yes, so finally, 10 sessions later, or a bit less, but 25 hours of work later, we managed to get to the point where we have a program and it runs beginning to, I think this is the end. Let's see where we got this 6th rep. So GDB doesn't, yeah, at exit. So it got to the end of the program. It ran it beginning to end in our emulation. And, you know, it's still not perfect. And we probably need to improve the output a bit. But I think we can take care of that in the next session. So I think we can commit this bug fix and also add a note. Yeah, the happiest moment on the 10th episode, and thanks for all the comments in the chat. So before we wrap up, let's just commit those changes. I actually don't want to remove all those console logs because they might be useful for debugging, but I think in the next session we'll start making them, like, define a flag or something to control those debug prints. Yeah, so fix the bug in the next instruction, and also remove the spin lock mechanism. It wasn't really, let's just write the commit number from the spin lock from, wasn't really needed. We only encountered that issue because of the bug in the next instruction. Cool. So committed, and we are good to go. And let's take a, so basically this entire session was, we had everything ready to run hello UART, and we had to find this very tricky bug in the next instruction, and also this bug with the writing to VTOR. And we spent a lot of time you know, like finishing all these small corners of getting GDB to work, so we could harness the full power of GDB. So I think we spent more than half of the time just nailing down all these like allow breaking from GDB. I see like we have exactly, wow, that's exactly 1 hour from getting this one to work until we got like the GDB one, the breaking in GDB, and so, and like then half more hour until we got breakpoints to work. But then once we finally got GDB to really work correctly, unlike last time where it sort of worked. Now it works, it's usable. Then things started to go really fast. Like this is like I think so. It's not exactly half an hour because we also did the spinlocks, but within an hour or so we figured out like this bug and the VTOR bug as well, and now we can finally move on. So I think in the next session, our first deliverable will be just to organize the code a little and to get it ready for a release. And then we'll just release a very first version of the library. We now achieved a milestone. We know it can run hello UART from the beginning to the end without any assistance, hands-free. So I think this is a good time to make a release of a very initial version of this emulation library. So we'll do that next time. And then, I don't know, we have all the tools that we need to start debugging other programs. So I will probably get some input from you at the beginning of the next session, but it would probably be either going into MicroPython. I will make sure we have a binary plus L file ready for the next time, or trying to implement some PIO. I guess that's the more interesting peripheral that the Pi Pico has. Or if you have any other suggestions, just hit me on Discord throughout the week and let me know if you have other suggestions to what we should do after we release this, organize the code and release this very first version of the RP2040JS library. So until then, have a great week and see you again next week on Tuesday. Bye-bye. Bye-bye.